Imagine this moment. Deep inside the Earth, where only the brightest minds dare venture, a giant machine is humming with power, about to unlock the universe and its deepest secrets. The air is filled with anticipation as scientists stare at their screens, ready to record the unimaginable. The discoveries awaiting us could reshape our understanding of existence. The Large Hadron Collider, LHC, has made another surprising discovery. The Higgs boson, a particle essential to our understanding of the universe, is heavier than we originally thought. The Higgs boson, sometimes called the Higgs particle, is a fundamental part of the standard model of particle physics. It forms when the Higgs field, a fundamental field in particle physics theory, is excited by a process called quantum excitation. In this model, the Higgs boson is the heavyweight champion. It is a type of particle called a scalar boson, which has no spin, no electric charge, and no color charge. However, it is very unstable and tends to decay into other particles as soon as it is formed. The Higgs field is like a cosmic tapestry that stretches across the universe. It is always non-zero, even in empty space, giving mass to all particles through the Higgs mechanism. It's as if the Higgs field were throwing a party, inviting all particles to join, giving them mass and breaking cosmic symmetry in the process. We owe this idea to physicist Peter Higgs, who along with a team of scientists proposed the Higgs mechanism in 1964. This revolutionary theory explains how particles gain mass and led to the prediction of the Higgs boson. It's like putting together a puzzle. If their ideas were correct, there had to be a particle with certain properties, and the Higgs boson confirmed all of these. The Higgs boson, often called the God particle, was discovered after 40 years of searching. In 2012, scientists finally found the rare gem thanks to the powerful ATLAS and CMS experiments at the Large Hadron Collider. They found a particle that matched the long-sought properties of the Higgs boson. The discovery was like finding the missing piece of the cosmic puzzle. This breakthrough was so important that the two leading theorists, Peter Higgs and Francois Englert, were awarded the 2013 Nobel Prize in Physics. However, it must be acknowledged that this important milestone was achieved through decades of effort and collaboration among many scientists. Between 1960 and 1972, a number of researchers independently contributed to the basic theory known as the Higgs mechanism. Fast forward to recent years. As the LHC continued its work and collected more data, scientists took a closer look at the Higgs boson and made a surprising discovery. Its mass is greater than 125 gigaelectronvolts, GeV. The revelation has caused a stir because if the Higgs boson is indeed heavier than predicted, it could lead to a rethinking of some fundamental aspects of our understanding of the universe. Does this mean we need to abandon the standard model and start over? Not necessarily. However, it does suggest the exciting possibility of new particles or forces that lie beyond our current understanding. The discovery adds another piece to the puzzle, one that could change the way we view the universe. The discovery of the heavier Higgs boson has revived interest in the Higgs field and its role in the formation of the universe. Even after the initial discovery, research on this mysterious particle has continued. In the future, research on the Higgs boson is expected to increase, especially during the third cycle of the LHC. This will be especially true after the completion of the particle accelerator and high-luminosity technology upgrades in 2029. This upgrade will allow the LHC to perform more collisions, giving researchers a greater chance of discovering unusual phenomena that deviate from the standard model of particle physics. CERN estimates that the LHC will produce about 15 million Higgs bosons per year after the upgrade, up from the 3 million it produced in 2017. This increased production could help identify different types of Higgs bosons beyond the standard model. Some theories propose as many as 5 different types of Higgs bosons, some of which are rarer than the basic Higgs boson. Even before these advances, scientists had found compelling evidence for the existence of the magnetic Higgs boson. But why is the Higgs boson so important? The Higgs field is unique. It is the only field known to permeate everything, giving mass to all other fields and particles. Understanding the Higgs boson opens the door to new discoveries in physics. For example, the Higgs boson could help answer questions about dark matter, which is 5 times more abundant than normal matter and is necessary for the formation of galaxies. We don't know much about dark matter, but it could interact with the Higgs field, revealing new insights. The Higgs boson may also explain dark energy, which is responsible for the accelerated expansion of the universe. This field could pave the way for the discovery of new physical laws and different universes. Additionally, the Higgs field is essential to our existence. Without it, electrons would not form atoms, resulting in a universe without stars, galaxies, or life. So although the discovery of the Higgs boson is a major breakthrough, its true significance may yet be revealed and could lead to new paradigms in our understanding of the universe. But the LHC search isn't limited to the Higgs boson. Researchers are looking for other unusual particles and evidence of dark matter. One of these theories is supersymmetry, which suggests the existence of superparticles, heavier versions of known particles. But despite its power, the LHC has yet to find solid evidence for the theory, raising more questions than it answers. The LHC is also exploring extra dimensions like those seen in science fiction movies. These dimensions could explain why gravity is weaker than the other forces. Some scientists believe that tiny particles called gravitons could reveal these hidden dimensions, changing our understanding of space-time. The search for these particles has had some success, but we still have a lot to learn. The discovery of one of these particles would be revolutionary, revealing new forces, new particles, and the structure of the universe. Even if we don't find these particles, the LHC will still provide valuable data that pushes the boundaries of human knowledge. Recent discoveries from the LHC have shaken the scientific world, revealing particles that defy the standard model. These unusual particles and decays suggest the existence of an important new force in nature. The LHCb experiment observed beauty quarks decaying in unexpected ways, suggesting the existence of a fifth fundamental force. This new force, in addition to the four known forces, could explain the formation of the universe. It could even lead to a grand unified theory, combining the weak, strong, and electromagnetic forces into one. This force could also explain the imbalance between matter and antimatter in the universe. Although antimatter is rare today, the early universe contained an equal amount of antimatter. This force could have caused the matter-antimatter imbalance that gave rise to our universe. The resumption of LHC operations will shed light on this potential new force. While this may seem far-fetched, it is not. The LHC has discovered particles that defy our understanding, such as the Higgs boson and tetraquarks. The potential for new particles, forces, and dimensions is immense, and we are only just beginning to explore it. The work of the LHC and its partners could unravel many mysteries and shape our understanding of the universe. Imagine you were in the control room when CERN scientists discovered the famous Higgs boson signal. This intense and moving moment is the result of decades of effort. Since then, the LHC has been running for 8 years, performing countless experiments. But why did it suddenly stop? Was it routine maintenance or a more serious problem? Follow along as we delve into the details of the LHC shutdown and uncover the truth behind CERN's mysterious actions. The Large Hadron Collider, LHC, is a testament to human ingenuity and curiosity, pushing the boundaries of scientific discovery to unlock the mysteries of the universe. Nestled deep within the Franco-Swiss border, this giant machine represents the pinnacle of particle physics research, designed to probe the fundamental building blocks of matter and the forces that govern them. Operated by the European Organization for Nuclear Research, CERN, the LHC is as much a scientific instrument as it is an engineering marvel. Spanning 27 kilometers in circumference, the circular accelerator uses powerful magnets and superconducting technology to propel particles to near the speed of light. As they travel through the LHC's complex network of vacuum tubes, they are guided by precisely controlled magnetic fields, accelerating them to energies never before achieved in a laboratory. The heart of the LHC's scientific mission is the ability to collide particles at unprecedented energies. These collisions occur millions of times per second, recreating conditions similar to those a fraction of a second after the Big Bang, giving scientists a glimpse into the earliest moments of the universe's existence. In the fleeting moments of these collisions, particles fragment into a series of even smaller particles, each interaction providing valuable information about the fundamental forces and particles that govern our universe. Detectors placed around the LHC collision sites act as high-resolution cameras, recording the trajectories, energies, and identities of the particles created in these collisions. These detectors, such as ATLAS, CMS, ALICE, and LHCb, are marvels of modern technology, consisting of layers of sensors, magnets, and sophisticated electronics designed to precisely measure the properties of the particles as they emerge from the collision sites. The data generated by these probes is massive and complex, representing petabytes of information each year. This huge amount of data is meticulously analyzed by international teams of scientists, engineers, and researchers who collaborate across borders and disciplines. The goal is to unravel the mysteries of particle physics and test the limits of our current understanding of the universe. One of the LHC's most important achievements was the discovery of the Higgs boson in 2012.